Hello Internet! I've been meaning to do a video about the Kalman filter for a long time, so finally I'm doing something about it. I'm gonna give my take on the famous Kalman filter, perhaps helping some of you or quite possibly just adding to all the confusion out there. I will assume you've heard of the Kalman filter before, perhaps you're studying it or trying to apply it to a problem. The full set of equations with matrix notation can be discouraging, it might look like some magic formula pulled out of a fairy tale. So here's the deal, I will show you the derivation in one dimension, so no vectors and matrices. I will use the statistical optimization approach, not the Gaussian filtering, and demonstrate a simple use case on a little toy example. To start off, we need a short recap on statistics. Keeping it perhaps extremely short, here are the rules you need to remember. There's the expected value or mean value, which is the value you can expect from a random variable. There's the variance, which is the deviation from the mean squared. There's the standard deviation, which is the square root of the variance. The covariance is similar to the variance but defined for two different random variables. It relates to how these tend to move together. Under linear operations, which means multiplication by constant gain and addition, the expected value scales up with the constant gain and adds up. The variance scales with the constant gain squared, and the variance adds up, with the additional correction for covariance, which is 0 if the two variables are independent. These statements are true regardless of the distribution of the random variable, as long as the distribution is, let's say, well behaved. So you don't necessarily need to assume Gaussian distribution to derive the filter, though I would like to get back to this topic at the end. So then, let's get to work on the Kalman filter. I'll be using the example of a small engine driving a generator. Let's say you want to measure the RPM as best as you can. You have two sensors at your disposal, a Hall effect sensor that directly counts rotations and the generated voltage output, which is proportional to the RPM. One returns omega m for measured RPM, the other omega v for voltage RPM. Both of these measurements are noisy. Normally you can reduce noise by averaging your measurements. However, their noise is not the same. The voltage-based calculation is 2 times as bad as the measured value. So would it be fair to average them equally? No, not really, but should you just discard the voltage then? That's not right either. It's worse, but not completely useless. So this is the problem of optimal interpolation between two noisy measurements. Let's say you want to interpolate between two readings, so multiply one by a and the other 1 minus a. This way, if both of them show the correct value, we're guaranteed to get it correct. We can optimize this interpolation by looking at the variance. Let's call the variance sigma v squared and sigma m squared. Sigma is the standard deviation. The variance of the estimate is then a squared sigma m squared plus 1 minus a squared sigma v squared. You can differentiate by the coefficient a, and with a bit of algebra you can get a equals sigma v squared over sigma m squared plus sigma v squared. This leads to a nice little formula. To combine two measurements, you scale them by the variance of the other and normalize by the sum of variances. Given our example of engine and DC generator, you measure plus minus 50 RPM with a magnetic encoder, and back calculating from the DC voltage you get plus minus 100 RPM. The true RPM is 1000, though we don't necessarily know that. So then, plug those values into our formula. Turns out you need to rely on the measured RPM by 80% and give 20% to the voltage. Now the question is, did this help or improve anything? We can look at the variance of the estimate, which yields 2000. The root of that is 44.72. Compared to the plus minus 50 of the RPM sensor, this is a little over 10% improvement. This is what it looks like with Gaussian distributions. You have two measurements, they have the same mean value, but their spread is different, one of them has twice the deviation of the other. You get two actual samples from each of these distributions. You calculate the ideal mixing ratio, in this case 80% to 20%, and that gives you a new sample. This sample has a distribution that will also be Gaussian, and the deviation is about 90% of the better measurement. It improved a little bit, but not by a whole lot. To be fair, having measurements of equal deviation does not cut the resulting deviation in half, only reduces by a factor of square root of 2, so about 29%. Another quick note, many sources show this graph like this with different peaks. I think this is the Bayesian approach. This represents your belief about the true value based on the measurement, but I'd rather not get into Bayesian belief propagation just yet. Taking a sort of outside perspective, the distribution that generates these samples has to line up, even when the samples are spread out. Now then, the estimate improved by 10% after the combination. Can we do better? The estimated RPM is also just a Gaussian, so if you get yet another measurement, you can combine it with the earlier result, right? Well, I'd like to do this justice by deriving the 3-measurement case. Then you can see exactly that the interpolation method is associative. You can combine 2 of them first and add the third one later. So get ready, because we need to do some math. We have 3 variables x, 1, 2, and 3. Their variances are sigma squared 1, 2, and 3, and they are independent from each other. Define our estimate as a times x1 plus b times x2 plus c times x3. To keep our estimate unbiased, we have the constraint that a plus b plus c must add up to 1. Take the variance of the expression and you get the a and b and c squared coefficients. The covariance terms are 0 due to them being independent. Now I hope you're not scared of the French, cause I'm gonna use the so-called Lagrange method, which is actually pretty nice. Define the Lagrangian as the variance above minus lambda times the constraint, and we'll start differentiating. You can see the pattern that for each coefficient you get 1 over sigma squared times lambda over 2. For the last one, it lets us combine all the other equations to find lambda over 2, and this yields us the coefficients. Now let me use sigma to the power of minus 2 to save some space here, and the expression for the estimated x is as follows. For each value x, you scale it by the inverse of its variance, and then you normalize by the sum of all inverse variances. And for the variance of the estimate, it's just the inverse of the denominator from above. It's actually the same formula as combining resistors in parallel, if you know electrical engineering. And now, to show you the association property, here's how it turns out for combining 2 values and then the third. As you can see, the term with sigma 1 and 2 cancel out, and we get the same expression as the one for 3 values. So say if you have 4 or more measurements, your options are: you can combine them in one shot, or you can combine the first 2 and then combine the result with the third measurement and then the fourth, and so on. The key idea is to carry the variance of the current estimate. This is the core, the heart of the Kalman filter. You keep track of the variance of your estimate and keep improving it by adding more measurements, either by getting more sensors or getting new samples in time. Now you've seen the optimal interpolation method, but we still need a few steps to define the Kalman filter. So far we had the voltage to RPM conversion outside of the filter. Now we'll move that inside the filter's framework. The second point is to formalize the error covariance that we carry from one step to the next. Here's how the Kalman gain and the estimation update step is defined. This part is not derived from anything, this is the definition. The measurement z equals the true state x times some conversion constant h plus added noise v. The estimation update is defined as the previous state plus the Kalman gain times the measurement minus the expectation of the measurement h times x hat. So unlike the interpolation gain from before, The Kalman gain is not a dimensionless weight factor. It also has to carry an inverse conversion factor for the dimensions to match up. For our little generator example, you don't need to convert voltages into RPMs, you can plug them in directly. The Kalman gain includes the conversion from volts to RPM. Let me derive the Kalman gain for estimating a constant. Some call this recursive least square estimation, not Kalman filtering, since it doesn't have the state prediction step that we'll work on later. First, let's rearrange the definition like so. Then let's introduce the difference between estimate and true value, which is then rearranged like this. We get 1 minus hk times the previous difference plus k times the measurement noise. Let's look at the variance of the estimation error. Since the noise v is independent of x and x hat, there are no covariance terms, and the variance is just 1 minus hk squared times the previous variance plus k squared times r. Let us introduce here the symbol p as the variance of the estimation error. The variance of the measurement noise is r. Now all we need to do is differentiate by k and solve for 0. This gives us k equals hp over h squared p plus r. This is structurally the same as the proper matrix equation, except we had much easier time with it with everything being scalar. You plug this back into the variance equation and you'll get p equals 1 minus hk times pk minus 1. Now look at the expression for k. If h equals 0, k will be 0. This results in no change neither in the state estimate, x hat, nor p changes. Sometimes you can get intermittent measurements and you might want to exclude them from the estimation. In certain programming languages, it might be easier to just set the h to 0 for a missing measurement instead of handling it with if-else conditions. When you move on to the vector matrix setup, the h vector or matrix can describe a direction, and the estimate improves in the direction of the h vector, while staying unchanged in all perpendicular directions. One other thing to note is that 1 minus hk is less than or equal to 1. P decreases all the time, which means your estimation gets better and better. This also means that the update gain k is getting smaller and smaller. As you keep updating, the relative worth of new measurements becomes lower and lower because their variance is much higher than what you already have. This can be okay for a constant parameter, though you might run into software issues if you try to run it for hours or days. Going back to engine RPM though, is it fair to say that it's constant? Here's how that looks on a graph. Something tells me this doesn't look right. So yeah, the RPM isn't actually constant. There are harmonic oscillations, small changes of RPM due to variation of timing, fuel injection, air intake, and so on. This leads us to the concept of process noise, system dynamics, and prediction. I'll model this generator with the following perhaps simplified setup. There's a throttle input U that represents a valve position between 0 and 1. We have a coefficient G that converts valve position to an expected RPM. Every second the RPM behaves in a way that it correlates with previous RPM by a factor of f. Omega k plus 1 equals f times omega k plus g times u plus wk. There is added randomness to the system in the form of wk. This is the effect of slightly inconsistent air intake or ignition timing. We'll be using the voltage measurement on the generator side, Z equals h times the RPM plus added noise V. Here's a simulated startup sequence of this engine. The actual speed has these vibrations, small random changes, and when we try to measure it via the voltage, there's added white noise. There is an ideal startup transient, which, well, does not exist but can be simulated in discrete time. The Kalman filter works in discrete time and it can only see the measurement and the simulated response. It will interpolate between these two to get as close as possible to the true RPM harmonics included. To see how this plays out, we need to investigate a bit deeper how noise and dynamic systems interact. Here's a typical exponential response from a first-order system, such as the one I used for the engine model. Now imagine repeating the same experiment with a random starting value and lining up the responses in time. All of them follow a similar trajectory, but the deviation goes to zero in a few steps. The variance of these packets decreases even quicker. I'm using the value f equals 0.5, so the value decreases by 50% every step. But remember, the variance scales by the gain squared, so every step it is down to 25% of the previous value. Next, let's add noise to the second step as well. This increases the spread because there was still a bit of randomness left over from the previous step. And then we add noise to step number 3 and so on. This is how randomness travels through the dynamic system. When applied to the engine example, it's not that the RPM is in a quantum superposition or anything, but rather if you repeated the same experiment over and over again, you could have gotten any of these values. And now this is what happens when you add the deterministic input alongside all this. Since our system is linear, there's linear mixing or superposition happening. The mean will follow the ideal response and the noise will be spread around it. The variance is defined as the deviation from the mean, so it doesn't increase just because we added a bias. You can see that the variance approaches a steady state value. I will name it pi just to differentiate it from the error variance p, and we can calculate its value as so. Pi equals q over 1 minus f squared. So, all that's left is to combine this with the estimation formula from before. When you're estimating a constant, the definition is that it doesn't change between time steps. When you're estimating a dynamic state, you need to simulate and adjust your estimate from one step to the next. This is called the prediction step. It is applying the simulation of the system to come up with the best guess of where it should be. So the true state changes by fx plus gu, and it also gets a bit of noise injected with w. The estimated state must follow it as best it can, so x hat changes by f times x hat plus gu. Remember that we know perfectly well f and g and u. All that is unknown is modeled by w. Now for the variances, the actual system got a bit of random disturbance added to it, so the variance around its own mean trajectory increases by q. Remember that the variance of the system pi is not the same as the error variance p. On the estimator side, we're keeping track of the variance of the estimation error. Because the true state's variance increased, the estimation error's variance also increases by the same amount. The process noise W is independent of both estimated and the real states, so we don't need to examine the covariance terms. Now we will combine the estimation update with the prediction. Instead of using the previous covariance pk-1, you use the updated covariance of the prediction. They call this a priori covariance, for it is before the measurement evidence. All this means that you can't rely on the true state to be constant between steps. You need to take into account that things change over time. Next, you apply the optimized Kalman gain to estimate the state value and update the error covariance. And that's the Kalman filter in a nutshell. One small remark here. When you're estimating a constant, the error covariance converges to zero. This time, the actual system is getting new randomness added to it every cycle. This also raises the error covariance p, so p tends to have some finite value. Also, I think I missed the subscript k here and there, but at least for this last part, it's there on all coefficients. This means the Kalman filter is perfectly fine with all of these parameters changing their values every step. The Kalman filter is all about making the ideal update in the moment. It does not need to care about the history of these states. Going from one dimension to the vector matrix setup, in short, it's the same but more. I can't go into details on this for this video, but if there's demand I might look into it. Before we close out, there's an elephant in the room I want to address, a normal distribution, aka Gaussian distribution. Here's the thing, the Kalman filter does not need Gaussian distribution, it does not depend on it. The core of the derivation relies on how variance and expected value propagates with linear operations. These rules are not limited to Gaussians. So the Kalman filter will give you the expected value and the error variance. You might run into problems when you try to use any of that for actual probability or confidence range. It is true for Gaussian distribution that 95% of values lie within 2 sigma. If you don't know the distribution, you can't make such statements on probability. Many people approach the Kalman filter as a special case of Bayesian filtering. Now, if you do that, the goal from the beginning is to define and propagate the entire distribution, not just mean and covariance. Now, in this case, Bayesian filtering collapses into the Kalman filter only for Gaussians. The question is, are you really interested in the full distribution? This is where engineering judgment comes into play. You need to decide for your application. You'll never get perfectly Gaussian white noise, but also it won't be far off from it. So, this has been the Kalman filter. I hope it helped some of you. I might come up with some follow-ups if there's any interest. Thanks for watching. Bye.